Hi everyone, my name is Artur Ghukasyan. Today we'll talk about my capstone project, design and construction of a wind tunnel for advanced particle flow analysis. My supervisor is Dr. Hracha Kocharyan, and today is May 21st, 2025. So essentially, I'm sure all of you are familiar with wind tunnels. They are mainly used for prototyping. Generally, when someone tries to mass produce a plane or a car, smaller model is tested through aerodynamic validation in such tunnels. Here we see a model scale aircraft testing in NASA subsonic wind tunnel. Uh, Moving on, tunnels can be classified into two general categories: open loop tunnels and closed loop tunnels. Open loop tunnels use ambient air. They exhaust it after testing. They are more simple, modular, and cost much less. And for our purpose of granular flow simulations, it's perfect and it avoids particle buildup. Closed loop systems, on the other hand, recirculate air and enable more tighter control of airflow conditions. They are mainly unsuitable for particles, requires much more complex filtration. The images show open and closed loop tunnels. Moving on, wind tunnels generally, as mentioned, simulate controlled airflow for aerodynamic testing. They are used mainly in aerospace, environmental, and particulate flow research. This project integrates dilute particle leaden flow into a subsonic platform that is sparse particle flow. It's designed for both flow visualization and force measurement later on. Here you can see an industrial grade tunnel which costs tens of thousands of dollars. The aim of this project was to create something much cheaper, and the idea is to design a subsonic open loop wind tunnel for dilute particle leaden flow, enable experimental validation of flows previously studied only in simulation, and use a simple injection passive collection configuration. Also, we aim to maintain modularity for ease of transport and experimental flexibility, ease of disassembly, etc. Moving on, this was the original hand-drawn sketch made by me. We have from left to right the entry fan box, the construction section, the test section, and the diffuser outlet. As you can see, or you can't see, okay. The contraction section just builds up pressure to organize like uniform flow inside the test section, and that's where our force sensor is located. And at point 6, you can see the injection tube, where from the particles will be injected. This was the initial concept. A lot of modifications have been made to this. The particle trajectories by diameter were studied in prior work. Last year's capstones by Ani Shahkyan and Anahit Doshoyan made CFD simulations of such flows, and they theoretically designed this wind tunnel. So basically, my capstone is the continuation of their prototype. Particle trajectories were analyzed for diameters 1, 2, and 3, 4, and millimeters. Particles with diameter more than 3 millimeters exhibit ground impact before exit, indicating limits for flow following behavior in dilute regimes. Initially, our experiment was set up for small silica gel particles, which were in the range of 1.5 to 2 millimeters in diameter. So this was used as numerical validation of what we're trying to achieve. The aim was to gain it experimentally. Since dilute flow analysis has never been studied in an experimental way, mainly all the papers study the dense flow of particles. Here is the cut section now. 4 modular sections were designed: inlet, contraction, test section, and the diffuser. Sheet metal was designed for cutting, bending, and welding, making the process of manufacturing as simple as possible. And flank joints were supporting the disassembly, as you can see between the test section and the construction section. There are flanks to allow ease of disassembly, and all the interfaces were aligned for seamless mating. These are some other CAD visuals. As you can see, there is a hole in the top view. On top, that's the placeholder for the injection tube, which was a steel tube of 300 millimeters length. Side view shows the other part where the test section is closed, and the close-up of test section and the flange shows the whole body. As you can see on the exit, on the rear part, we have some small box beneath it. So essentially, when a mesh is put on the end, this will allow particle collection to happen right below the box, and the inlet section will contain the fan, which is 80, which weighs 80 kilograms almost. So this is what's been done. Mechanical assembly. Initially, the panel fabrication. All panels were made from 1.5 millimeter stainless steel sheets. CNC cutting was used from the initial 2D sketches from computer-aided design. SolidWorks was used for the design. And edges were cleaned and bent to specification. Flanges enable the bolt-on modular connections for the two sections and ensure precise alignment and ease across the sections. Hole placement was also verified after bending. And this is the test section. Plexiglass panel was manually sealed onto the test section steel frame, bonded using construction adhesive, and it was allowed to fully cure for a day about. And after that, foil tape was used to seal the edges just to cover the adhesive seams visually. The goal was to just visualize the flow from the side. And here you can see the injection tube, which was a steel tube, 50 by 50 millimeters, length of 300 millimeters. The pipe was welded vertically into the construction section, and the lower 200 millimeters of the pipe extended to the inside of the construction section. This length was achieved through CFD simulations by the prior work, and 200 millimeters is the exact length that allows a uniform flow through the test section. Removable mesh frame was bolted on the later part, on the rear box, to allow collection of the particles. It's from aluminum. It's a removable frame, so basically it's just bolted. This is the force sensor that was to be used. The TIS-3F is a strain gauge-based 3-axis sensor. It measures the forces along the XYZ axis, and it rates 100 kilograms of load with high linearity and repeatability. It will be installed between the test section for load measurements. The sensor has been received, however, the integration is still pending. It will be used in the future phase for aerodynamic force acquisition under particle lead and flow conditions. And here are the enclosures and the fan mount. Two steel enclosures fabricated to support the structure. The inlet box contains the fan, and the rear box contains the mesh, the collector mesh. Corner profiles of 304 grade steel were added under the bigger box to reinforce base structure. Fixed caster wheels were installed for alignment and for mobility. Essentially, this allows movement through all directions. The total weight of this tunnel is about 90 kilograms, and the caster wheels support the weight easily. So, final assembly and structural validation. All segments were joined via bolted and flank connections. No visible gaps were observed, or actual misalignment as well. It was supported by two rigid enclosures with fixed caster wheels, and structurally was validated and currently is ready for further airflow and sensor integration. Here is the dimensions of the obtained wind tunnel. As you can see, it's over 2.5 meters long, 1 meter in width and 1 meter in height or so. Unfortunately, I was not able to bring it here. because some of the doors are 80 centimeters wide. So generally, space was the most major issue that I've encountered during this project. Moving on, to conclude, we developed a modular, low-speed, open-loop wind tunnel for dilute particle lead and flow experiments, constructed using stainless steel and plexiglass through cutting, welding, bending, and bonding. Modules were aligned using flank interfaces. Other components were permanently fixed. The system is now ready for experimental operation and flow diagnostics. Next steps include future work. Installing the eggshell fan and flow sensors, running airflow tests to assess uniformity and turbulence across the whole wind tunnel, and conducting particle injection experiments with varied conditions. The future work, if you can say it like that, is comparing the results with CFD model for clear validation. This project was a research initiative by Dr. Ghukasyan, and we had a strict budget for this, and we succeeded with it. I would like to express gratitude to Dr. Hiracha Ghukasyan, whose guidance, patience, and sharp feedback shaped every part of this project. Many thanks to Alexander Hakopyan, who's here. Hi, Alex. For his steady support and encouragement. And big thanks to Aram Hovanesyan and Gori Soyan for the hands-on help, for the questionable advice, and for the faith that it will hold. Thank you very much. Any questions or comments or any feedback is welcome.
Can you carry us through generally, or pick specifically, the most challenging or difficult, or I don't know,
difficult process?
Design like parameter. In other words, you mentioned it was this heavy or this long or this wide with this material, but what went into the decisions?
Okay,
like,
I'll start.
I mean, I don't know, if you want it to be mobile, make it 80 centimeters wide, or if you want to, or if you, are there issues about boundary layers or others that went into the decision about materials? Or I'm a little curious about the decision-making process. And maybe others are very curious, but I'm less curious about the actual like hardware part list, you know, what kind of aluminum this is or not. And I'm more interested in some of the judgment and design
considerations,
questions. So you're free to answer however you want, but I'd like to hear a little bit about that.
Okay, essentially, initially, I think the material selection has been changed 3 or 4 times. Initially, because at the beginning, we tried to build something that is not as heavy. So it's easily transportable even without wheels. Initially, some types of wood were considered, but then wood has other problems with bending, with brittleness, and etc. And also construction-wise, having 2 woods connected at a certain angle in a vacuum is quite hard to accomplish. That's why we moved initially to aluminum sheets. Then aluminum sheets proved to be less structurally resistant to any bending, or in general it was harder to work with aluminum than it is with steel. Because even during the welding process, different types of welding is used for aluminum and for steel. Also, some financial limitations were encountered during this. So I tried to be as budgeted as possible, but it was hard to accomplish. From other design considerations, initially, as you can see in this right part, there's this frame at the exit. I don't think the bolts are visible, but initially it was considered to just put a mesh, tape it somehow. But after considering other options, we decided to move on with this. This allows more expandability in future in terms of experiments. Also, initially all parts should have been flanked, sort of. But that might have caused a lot of misalignment. I think that's it pretty much. The pipe for the tube injection was bigger as well, but since the particles were so small and we didn't need so dense particle flow in the end, we decided to make it smaller.
Can you tell us a little bit about your design calculations, i.e. the speed of operation, what type of test articles you can test in these wind tunnels?
By test articles, you mean test cases or?
The size of the test articles that you can actually measure, the effect of the geometry of your wind tunnel, because it's a rectangular section, cross section, and various considerations have to be made
I see.
based on your type of test articles.
You see, initially the diffuser section should have been longer, but because of space constraints, it was shortened.
My question is the velocity range.
Velocity range is subsonic, up to 15.15 meters per second. There was actually a fan that has been procured by AUA.
Subsonic is up to 340 meters per second.
No, I meant the fan that we have. I'm sorry.
Velocity range. What is the maximum velocity that you can have in the wind tunnel?
I didn't calculate the maximum velocity, but I'm sure it will sustain the 15.5 meters per second, or even higher, much higher, I think.
It was calculated by the previous group.
Yes, actually, it was prior work.
It can go up to 100 meters.
And conceptually, the view of the tunnel was initially designed by them. So my task was more of implementing this, actually.
So you haven't carried out any computations. Your job has been as an engineer to take whatever they've come up with and build it.
Yes.
So you basically built it and not done any analysis with it because you haven't run it.
No. The object was just building this.
Building it.
And also, actually, these models were not present. So essentially, these boxes were not initially designed by them. This allowed for more structural modularity, so I can just put it on the ground as well if I want. But initially, the areas, so basically, let's say in the construction section, there is this smaller area and the bigger area. The ratio was decided by them through computer experiments. So my job was to sustain those parameters. That's it.
And go back to your original picture, the one that you showed.
This one.
when NASA,
Yeah.
No. Go back even further. One more.
Yes.
Yeah, that one. See how long that test section is for force calculations, because you keep saying force calculation. Particle laden flows and so on, that's different. But the test section that you guys currently have in this wind tunnel, while it can be used for certain types of applications, it probably isn't good for the type of applications where you really are going to put some sort of a model.
This is just some sort of inspiration and introduction to everyone who's not familiar.
What do you envision, so coming back to Avetik's question, what do you envision testing in this wind tunnel? In that short test section, which
let's say a
will not have,
much smaller
uniform
prototype.
flow. Maybe a uniform core, but probably not a uniform flow.
I'd say a smaller prototype would be.
Mostly educational.
Education.
Yeah.
Flow, like how flow.
Like visualization.
Yeah,
Flow
kind
visualization.
of. And besides that, like the particle part that we have mentioned, at least I don't know anyone who has done it. So and it's a very challenging and risky project, and I think you need to be a bit crazy to do something like this. But since day one, that the idea came to me, I was debating whether I am crazy enough to try. Eventually, I figured out I am crazy enough. So we went with it. So for that, for the particle flow, we don't really need that much accuracy. And for anything else, obviously this is never going to be scientific, but it's going to be educational. So let's say it's going to be used for like several experiments with particles, and after that it's going to be educational. So you will see, whoever will be present tomorrow, you will see many different UAVs that are designed by our students as their capstone projects. They design airfoils, they do some numerical analysis, but they don't do an experiment because we don't have the capabilities. With this, we will have the capability. Of course, again, it's not going to be scientific, it's going to be educational and, for testing.
Allow me to add something. So it's not just that Hracha is crazy. It's that when we hire, we look for crazy people here, because if we don't have big equipment budgets, we outsource our procurement to our students.
Exactly.
I'll stop there.
Are you aware of other wind tunnels operating in Armenia?
No, I'm not really aware. I don't have.
Quite a few.
What? Excuse
There
me.
are quite a few wind tunnels.
Yeah, I've heard some companies, engineering companies, do have them. But
We try to get in touch with them, get their experience in designing and building this.
I actually didn't have the network capabilities at the moment, but let me add also something like this particle tube also allows like adding just smoke in here. So if you put some smoke generating device, any kind of even a simple vape, it will visualize the flow just for mini drones or mini car models that are to be like engineered during further capstones at AUA.
If I can add my 2 cents, which is usually worth less than a penny, but last year's group spent maybe 6 months on their capstone. He spent 6 months on his capstone trying to build a wind tunnel. I think if anybody's going to pursue this, I truly think that AUA can probably build a better tunnel, which can be used for many things. A slightly better tunnel. And I think it's worth the effort, because right now, even though a lot of people are putting tunnels together, literally, I wouldn't trust any of those tunnels to have the type of flow which is necessary to calculate flows over UAVs, wings, and so on. It'll be very nice to produce color pictures and photographs and so on, but if we're really going to design something using this, with a little bit of tweaking, I truly believe we can get there. It just requires a little bit more tweaking, some thought about how long the test section has to be, and so on and so forth, but it's not that difficult. You guys are mostly there. You've done a lot of work. It's very commendable, but I would like to see something which is slightly more scientific. Let's put it that way. And we can do it.
So let me jump in.
Closer to application.
Let me jump in with the kind of facetious comment I made earlier, the humor, maybe good humor, bad humor. To maybe take a step back from everything we heard and make this comment. So our goal actually is not to build commercial or viable or production ready or scalable, wind tunnels. Our goal is the educational part, full stop. Now, that we are designing and now constructing educational grade, or if that's a term, tunnels that maybe with a little bit more tweaking could have broader applicability. I would actually flip your comment or question on its head and say, look, it's a group of students. How many wind tunnels have you built before you? None. Okay.
Let me think.
And how many wind tunnels have the 2 kids designed last year before? None. Right. So the purpose of our whole educational program is to get your feet wet. First time in the swimming pool kind of thing, not necessarily win the Olympic gold.
This was actually my very first mechanical assembly of this scale.
Right. Yeah, I don't know that, but it was a guess, and I guess I'm right. So my point is that I think that if these capstones are a great opportunity if companies which have invested in these wind tunnels and want to see activity like that's, and I know it's not a one-way street. It's our job to reach out as well. But I just want to use this as a platform, as an open invitation to all those companies who are interested in collaboration. I think I know I speak for the entire ecosystem here that we are likewise interested in. Yes, of course, I think there's a lot to echo the thought to be done in collaboration and by extension of any given class project or capstone that could evolve into something bigger, brighter, shinier, well, whatever it might be. So I think that's a healthy step in the right direction, and by no means the last step in that direction.
Alex,
Yeah, sure.
Alex?
Yeah, can you hear me?
Yes.
I do. Yeah.
We cannot
I
hear
just
you.
wanted to ask this. I know you're focusing more on the actual building and material choices and applications of this theoretical design. My question is the particles. What materials for the particles have been considered, and sort of what is the hardness range? Well, I know you talked about size that was discussed by Anahit and the previous capstone group, but what is the hardness or sort of material choice for the particles? Because even given the scientific, non-scientific educational aspect of it, have you thought of basically what is that material such that later you don't have the viewport getting scratched to the point where you don't even see your model, right? So has that been taken into consideration, and if so?
Sure. It has been. Actually, it was quite challenging to find appropriate materials for this, but just for prototyping, silica gel particles were considered. I actually procured 1 kilogram. Essentially, they're not as hard as I think they should be, but they are not as hard enough to scratch or dent the wind tunnel from the inside as well. Initially, it was considered that we add some material inside the wind tunnel to ensure that given like high-speed particles, which are harder, do not dent the wind tunnel. But we scrapped it off because I couldn't find any more appropriate material for this at the moment. Some other particles were considered like whole wheat or buckwheat, grechka, yeah. But they're not as granular.
1 millimeter in size.
Yeah.
You said 1 to 3 millimeter that your target particle size, right?
No, it can be less than 1 millimeter as well, actually.
So actually, last year's project also addressed that problem. It wasn't about the material property itself, it was just the density, like how, for different densities, how the particles will behave. But again, Artur will not have a good answer for your question because we haven't addressed it.
Out of scope.
Ralph, just quick question you might not be able to answer. Do we know what the volume loading of the particles is inside the screen? So the volume fraction roughly.
It's also going to be very different. Like again, last year we have examined it. We need different values.
What's the maximum that you're shooting for? Like 10%, 5%?
No, I think even more.
More.
But I don't remember what we had last year. We have addressed that question last year.
More questions? Or we should proceed? Thank you all.
Thank you again. Thank you very much.